You are live now.
Good evening from India. This is the second lecture of day 4 of International Virtual Workshop on Global Seismology and Tectonics. I would like to thank each and every one of you for participating in large numbers and raising the bar and standards of the event. I hope everyone is keeping in fine during this COVID-19 pandemic situation. I'm concerned about the recent rise of COVID-19 cases in few countries. During these tough times, let us not forget the sacrifice and hardship undertaken by the health workers across the globe. Coming back to today's session, I'm very excited that IBWGST also features scientists from Global Earthquake Model Foundation. It is a non-profit public-private partnership that drives a global collaborative effort to develop scientific and high-quality resource for transparent assessment of earthquake risks and facilitate their application for risk management around the globe. 3 sessions have been dedicated to GEM, and the first one shall be presented today by Dr. Kendra Johnson, who is a seismic hazard scientist. The topic of today's lecture is Introduction to Probabilistic Seismic Hazard Analysis, PSHA. Before her lecture begins, may I request our session chairman, Professor J.R. Kyle, to say a few words. Over to Professor J.R. Kyle.
Thank you, Shantanu. Thank you so much. Good morning to you, Dr. Kendra, for being with us today evening in India. We really look forward to listening to you. It's a very important topic for all of us. And we're again so grateful for kindly accepting our humble request to be with us in this workshop. Thank you so much. So over to Shantanu, please.
Thank you, sir. Now let me read out a short biodata of Dr. Kendra Johnson. She is a seismic hazard analyst at the GEM Foundation. Her primary roles are to develop probabilistic seismic hazard analysis at national and regional scales, assist in developing tools and workflows for building and testing seismic source models, help to maintain the global hazard mosaic and support its users, and to develop PSHA training materials and administer PSHA and Open Quake engine training sessions. Dr. Kendra completed her education in Colorado, earning a BS in Geophysical Engineering and PhD in Geophysics from the Colorado School of Mines. She developed an interest in earthquakes as an undergraduate when she helped to build the US Geological Survey SecMap Atlas 2.0. The research interest of Dr. Kendra Johnson, apart from seismic hazard analysis, includes regional moment tensor uncertainty, paleoseismology, geochronology, and the etc. She has authored several high-quality research papers on seismic hazard assessment and earthquake slip mechanism. I would end it here. This space is all yours, Dr. Kendra. Thanks again. Over to Dr. Kendra.
Okay, thank you very much for the introduction, Santanu. And I think you've done a good job of introducing the GEM Foundation. So I'll just go ahead and jump right into the talk on Introduction to PSHA. So as you've heard, the GEM Foundation is a nonprofit public-private partnership, and we're working with the goal of creating a world that is resilient to earthquakes. And our core values listed here, we aim to accomplish these by developing and providing open source softwares and models for hazard and risk calculations, in particular pertaining to earthquakes. And in addition to this, we're maintaining a global coverage of hazard and risk models that are formatted for that OpenQuake engine. And we also aim to build the global capacity for addressing seismic risk. And we do this in part by developing and providing tools and trainings that help provide others with the ability to do PSHA on their own. So we're happy to include this lecture series as part of those core principles. So this is the first of 3 sessions provided by the GEM Foundation, 2 in a row, the first one today, Intro to PSHA, and tomorrow will be the second lecture that goes more into the building the different components of a PSHA input model. And then finally, next week, there will be a 3rd lecture, an introduction to the Open Quake engine. So we'd encourage you to attend all 3 of these lectures if you're able to. So pictured here is the global seismic hazard map produced by GEM using the global hazard mosaic. And this is a mosaic of models that are provided by different partners with GEM, ranging from projects to individual institutions that have developed models for their respective regions or countries. And throughout this presentation, I will be using these models to provide examples of that demonstrate the different components of a PSHA model. So just a brief introduction to how this talk will be structured. The majority of the talk is focused on PSHA concepts, starting with the hazard integral and the main components of a PSHA model, and also discussing the different outputs that come from PSHA and their applications. And then I'll finish by giving a preview to a couple of the models that GEM is working on currently, one covering the Dominican Republic and one covering China. So the concept of PSHA arose from the need to reduce the subjective judgment applied by experts when they're performing seismic hazard calculations, but while still recognizing the aleatory or random nature in the earthquake processes. And so to summarize this, PSHA has come to calculate the likelihood of experiencing a certain level of shaking higher than some certain ground motion level during an investigation time T, some time of interest that's pertinent to the hazard application. And there are a few different ways of expressing PSHA results. The first is the annual rate or frequency of exceedance, so the number of occurrences per year of ground motions that exceed the level of interest. The inverse of this is a return period, which is the time interval between occurrences. And the final expression is the probability of exceedance, or the likelihood over a given time period. And the table at the bottom of this, this slide here shows some of the common values of each of these expressions that are used in PSHA applications. So you'll be seeing these numbers a few times throughout this presentation. So I'll start by introducing the hazard integral. And this is the mechanism used to consider all the possible seismic sources that may cause damaging ground motions at the region of interest or site of interest. And the solution to the hazard integral is a rate, lambda, at which a ground motion of some intensity metric exceeds a threshold x. And so this is a set of values of x usually, and each one has a corresponding rate or a probability. And this is actually the sum of multiple integrals that each correspond to a seismic source and consider the magnitude dependent occurrence rates of all the earthquakes that that source can produce. This is done by converting the sources into ruptures, earthquake ruptures, that may occur of all magnitudes and distances from the site. And for each rupture, the probability that a ground motion level will be exceeded at the site is computed. So the integral takes all of these ruptures and all of these ground motions together and then sums the sources. And this is the result of a single hazard curve. So one example of a hazard curve is pictured here on the right. And just to start orienting you with what a hazard curve looks like, the x-axis is showing the intensity measure level, which could be a variety of different things, PGA, PGV, and we'll go over those parameters a little more later in the presentation. Sometimes it's shown on a log scale as it is here, but it may also not use the log scale, whereas the y-axis is using one of the expressions, in this case, the annual probability of exceedance in log scale. And each hazard curve is corresponding to only a single scalar metric, indicating the level of ground shaking, and corresponds to only a single site with a single site condition. A few different probabilities of exceedance are indicated on the figure here, showing the regularity of ground motions that are considered for different building types. So in a qualitative form, this is indicating that more precaution might be taken for nuclear power plants than hospitals or schools and then normal dwellings. So how do we reach these hazard curves? We'll go through each of the main components of a PSHA model, which includes three main categories. There's the seismic source characterization, which includes one or more source model that independently represents all of the seismicity that could impact the region of interest. The second is the ground motion characterization, which is one or more ground motion model, so an equation that is taking those ruptures permitted by the source models and converting them into a ground motion level. And finally, the epistemic uncertainty in both of these two components is accounted for using logic tree structures. And we'll go into a little more detail on what epistemic uncertainty is once we reach this part of the presentation. So starting out with the seismic source characterization. To review, one seismic source model is the total of all the sources that might impact the hazard at a site or the region that the model is interested in. And each seismic source is a simplified description of something that occurs in nature. So it's something that can be easily represented using a set of coordinates and parameter values that represents something more complex, such as a fault. Each one of these seismic sources is characterized by the parameters that are necessary to evaluate the hazard integral. So breaking this down into three main steps. The first is to identify the earthquake sources that are relevant to the site or region. The second is to characterize each source according to these properties that are necessary. And then finally, to account for the epistemic uncertainties in 1 and 2. In principle, the first two steps comprise a complete source model, and so this is sufficient to evaluate the hazard integral. So how do we identify earthquake sources? We'll start by kind of zooming out to look at the whole globe and dividing it into main tectonic regions that are capable of producing earthquakes. So some of the major structures that we want to look for within the area of interest are plate boundaries, in particular convergent boundaries, such as subduction zones, continental collisions. We know that these can produce large or frequent seismicity. Also continental transforms and oceanic transforms, and to a lesser degree in terms of proximity, mid-ocean ridges. There are also sources away from the plate boundaries where earthquakes can occur. So intraplate earthquakes within subducting slabs, or also within the shallow crust, typically more so in active crust than in stable crust. There are also deep non-subduction sources and volcano sources. Zooming in a little bit to identify more specific structures, active faults are a super useful way of determining more precisely where an earthquake could happen. So active fault databases that include mapped faults that are deemed active and can be characterized using a few specific values such as the slip rate. We'll go into that a little bit more later on in the presentation. And then finally, earthquake catalogs. These show where earthquakes have occurred in the past, and so in theory, there are also locations that earthquakes could occur in the future. They also give us more of an indication of the rate of seismicity that's produced. And this is one of the most important data types used in producing a PSHA. So once we've identified the seismic sources, what are the main characteristics that we need to assign to them? So first and foremost, the position and the geometry of the sources. So actually creating some sort of physical representation of them. Secondly, the magnitude frequency distribution, which indicates the rate at which earthquakes of each magnitude can occur. The tectonic region that the earthquakes are occurring in, which impacts the way the ground motions propagate. A magnitude scaling relationship and a rupturing mechanism, which help the calculation engines convert the sources into ruptures. So starting out with the source positions and geometries, it's important to know the main source typologies that are used in PSHA. And the first on the left here is faults. And these are 3D surfaces that are used to delineate where a rupture occurs. Secondly, we have the diffuse or distributed seismicity sources, and these are for earthquakes that are known to occur, but they can't be represented as easily by a specific structure. So what are the advantages and disadvantages of each? Starting out with fault sources, these are ideal because they correspond to a physical structure that exists. And so when we model earthquake ruptures on a fault, the geometries and positions are more accurate. So some of the common uses for fault sources are subduction interfaces and crustal faults, places where there's evidence of earthquakes having occurred before and that were large enough that we were, or frequent enough that we're able to really delineate a structure using that evidence. The requirements are to have a known or well-approximated 3D surface that can be used to represent the fault coordinates. And additionally, we need some sort of data, either seismicity or slip rates, perhaps from geodesy or from paleoseismology, that can be used to help make estimates of how productive these earthquake sources are. So the limitations are that infrequent and lower magnitude earthquakes usually don't provide sufficient information to meet these requirements. So, for example, crustal earthquake surface ruptures are not very common for earthquakes of magnitudes under 6. And so, even though we know they're occurring on faults, we're not easily able to represent the fault with a surface. Additionally, when earthquakes are infrequent, there may be geologic processes or climatic processes that erase the evidence of the events before we're able to use that data. So a couple of examples of fault sources in PSHA models. This is from the model covering Papua New Guinea that's kept in the mosaic, and showing the subduction interface sources that are used for the New Britain and Solomon subduction interfaces. And the top two panels here are showing the geometry taken from SLAB 2.0, which is a USGS product that has characterized the subduction zones globally, as well as the seismicity data. The seismicity data that's showing past earthquakes that have occurred near the subduction interface. So together, these data are sufficient to create a fault surface that can be used as a source, a fault surface and a productivity that can be used as a seismic source. And so that source is depicted in the bottom right figure. A second example is of crustal faults. And this is taken from the PSHA of the Philippines, which used the fault database provided by FIVOLCS, the geophysical agency in the Philippines, which provides surface traces as well as slip rate data for faults crossing the whole series of islands. And each of these faults was converted into an individual fault source to be used in the model. So when we don't have sufficient information to use fault sources, instead we can use distributed seismicity. And so this is useful when we can more easily constrain the seismicity to some sort of zone or volume. And there are two main types. The first is area sources. These are polygons within which we assume that the seismicity is constant, both in terms of the rate, it has a uniform rate, and the major properties that are used to produce the ruptures are consistent across the whole volume. Second is smoothed or gridded seismicity, which is similar to an area source, but instead of using a uniform occurrence rate across the polygon, there is smoothing based on the locations of past earthquakes so that the rates become more likely close to areas where we know seismicity occurs. So these are commonly used for the shallow crust, subduction intraslab events, and other regions where small earthquakes are frequent or where strain is observed. So some examples of distributed seismicity. To start with, we have the area source model used in South Africa. And on the left, we see the plate boundaries that are impacting the area of South Africa, as well as the recorded events. And there isn't a lot of seismicity data here, so there may be insufficient data to create a smooth seismicity model. Instead, they use the area sources, so the figure on the right here, in which they delineated polygons around some major structures. On the contrary, this is the model for South America, zoomed in on the region of Colombia. And the red traces are showing fault sources, but there's also known to be off-fault seismicity in these areas, or off the mapped faults. And so this seismicity is modeled as gridded point sources with smoothed rates. So overlaying the seismicity on this plot, you can see that many of the earthquakes are occurring near the faults and also in the areas where the occurrence rates, which are colored in the warmer colors, are higher as opposed to away from the earthquakes where the occurrence rates are modeled to be lower. So once the source geometry and position is defined, magnitude frequency distribution, or an MFD, has to be derived. And this is what indicates the rate at which earthquakes of each magnitude are occurring. So plotted here are three of the common types of magnitude frequency distributions. The first is the Gutenberg-Richter relationship, which is a negative exponential, and it's indicating that a source produces smaller magnitude earthquakes more frequently than it produces larger magnitude earthquakes. The A value is indicating the rate of all earthquakes, or the productivity, and the B value is indicating the relationship, the relative distribution among the magnitudes. I'm also indicating on this plot a value of M min and M max, where M max is indicating the largest earthquake that a source can produce. So here we're showing an example of magnitude frequency distributions for central Italy, taken from the SHARE project that covers Europe. And to the right, we've plotted three MFDs that are corresponding to different area sources. And the MFD in red is showing higher values of seismicity, higher rates of seismicity than the one in green, which is showing higher rates of seismicity than the one in blue. And in the central plot, we can see how the seismicity varies among those three sources, the highest rates being in source one, plotted in red. The second type of magnitude frequency distribution is a characteristic MFD. And this is a type of MFD that assumes sources produce earthquakes of only one magnitude or a small range of magnitudes. And so this is an example taken from Canada's 5th generation seismic hazard model and corresponding to the Cascadia subduction interface. And they've used a magnitude frequency distribution that is similar to a Gaussian distribution shown in blue here. And this is showing that the most likely earthquakes are concentrated at about magnitude 8.9 to 9 with a slightly less likely chance between 8.5 and 9.2. Sometimes, oftentimes, magnitude frequency distributions are represented as cumulative rates instead of incremental rates. And so this orange plot here is showing the rate of earthquakes larger than the magnitude bin indicated on the x-axis. The third type of MFD is a hybrid type, for example, by Youngson Coppersmith. And this is indicating that most of the earthquakes are thought to occur in that characteristic range. However, a lot of, or some portion of the seismic moment is allowed to occur in small earthquakes as well. And we'll go into more detail tomorrow in the lecture on building a PSHA input model on how we actually constrain these magnitude frequency distributions. So this slide summarizes the remaining properties that need to be assigned to a source in order for it to be complete. And so the remaining parameters that impact the rupture geometry are the rupturing mechanism, which is indicating the strike and dip, so the orientation of the rupture plane in space, and the rake, so the relative motion of the two blocks on either side of the fault. There's also a magnitude scaling relationship that shows the correlation between rupture dimensions, such as area or length, and the magnitude. So in short, that the larger the fault, the larger the earthquake that can be permitted. And so these are used to construct the area of the rupture that that's produced. There's also a rupture aspect ratio that's indicating the shape of the rupture, whether it's closer to a square or more of a rectangle. The seismogenic depth limits and the hypocentral depth in the case of distributed seismicity. So constraining the layer in the Earth's crust where these ruptures must be confined. And then finally, each source is assigned to a tectonic region, which is used more in the ground motion component in order to indicate how the seismic waves will be propagating. So now that we understand the main characteristics that must be assigned to an earthquake source, we'll take a look at how the hazard integral uses these. And the first step is that the sources must be converted into ruptures. So the different properties of the earthquake sources that are defining the locations and the rates, as well as the dimensions, are used to create this distribution of ruptures of all magnitudes and all distances for that respective source. So this following animation shows an example of how this would occur for a seismic source. And I will clarify that this varies a bit depending on the calculation engine that's used, but the premise is similar across the board. So using the MFD, as well as the rupture aspect ratio and the magnitude scaling relationship, ruptures are produced that occur on a fault plane. So the inset here shows a series of black dots that have converted the rupture plane into a mesh, and those mesh points are used with the scaling relationship and the ratio to produce a rupture of the size corresponding to each bin in this magnitude frequency distribution. And so first we see just one rupture, but these are actually floated all along the fault until the entire fault is filled with ruptures. Then this is repeated again for each magnitude. So the higher magnitudes correspond to a larger rupture area. And again, this is covering the entire fault. So this will be discussed a little bit more on Tuesday's lecture about the OpenQuake engine in terms of how the engine itself uses these. So coming back to the steps that are required for seismic source characterization, we've now seen how to produce one seismic source model. So we've identified the earthquake sources and characterized each so that the hazard integral is able to evaluate them. The final step, accounting for epistemic uncertainty, will be covered in the logic tree segment. So the next component is the ground motion characterization. And to review, this is one or more ground motion models, which are used to predict the ground shaking that will occur when the ruptures modeled in the source model occur. And the way that this exists in the hazard integral is that a probability distribution is generated for each, or depending on each rupture's parameters. Then the output is the rate at which the ground motion will exceed a certain threshold. So let's start by looking at the ground motion parameters that we use to quantify shaking hazard. And four of the common intensity measure types are listed here. And the first two are corresponding to peak ground velocity and acceleration. And in PSHA, we're often more interested in the peak value that's occurring during an earthquake or during a period than the entire waveform. So that's why we're looking at only the peak ground velocity or acceleration. We're also interested in the spectral accelerations that are experienced by structures with different natural vibrational periods. So that's called the spectral acceleration as pertains to each period T. And then finally, there's a discrete scale, the macroseismic intensity, one of which is the modified Mercalli intensity scale, which uses Roman numerals rather than a scientific unit. And this indicates the severity of earthquake effects. So let's look at the important variables that are impacting the ground motion levels that are forecasted by these Gmpes. So the first is the earthquake magnitude, and as it increases, so do the ground motion levels. As site to source distance increases, typically the ground motion levels will decrease. The site conditions can also have an impact on the observed ground motion levels. So the shallow geology, the surface conditions, the basin structure, as well as the tectonic region type. So distance can be measured a number of different ways depending on how the ground motion model has defined distance. And the figure to the bottom right is showing a number of different metrics that are common in ground motion models. So the thick black line is indicating a rupture plane, which has been projected to the surface with the light gray line. And some of the most common metrics are the RJB distance, which is the horizontal distance between a site and the surface projection of the rupture. The distance RRUP, which is just measuring directly the shortest distance from the site to the rupture. And finally, RHypo, which is the distance between the site and the hypocenter. There are a few other metrics listed here, and sometimes some other geometry aspects come into play as well. So ground motion prediction equations are empirical models that are used to compute a scalar parameter value indicating the shaking intensity using one of the intensity measure types that we've defined. And a Gmpe yields a parameter value as a function of a set of explanatory variables. So the magnitude, the distance, and all these different parameters that we covered. Additionally, there's a random variable here called delta, which indicates that there is some aleatory variability within the ground motions that are observed for earthquakes that have common parameters. And so this is demonstrated in the figure on the left, where the intensity measure level is plotted against the source to site distance. And the median, the solid black line is showing the mean prediction. However, the observations are scattered about the mean. So here we depict an example from Abrahamson et al., which is one of the numerous ground motion models available. And in addition to the terms that are already been mentioned, this one includes a style of faulting terms. So whether the earthquakes are having a normal mechanism, a reverse mechanism, or otherwise. There's also an aftershock scaling term, a site term, the depth to the top of the rupture, and a term for whether the site is occurring on the hanging wall of the fault. We won't cover how GMPs are selected for PSHA until tomorrow's lecture, but to give you a preview, there are hundreds of GMPs that have been developed for numerous different reasons, for different tectonic region types, different geographic regions, different intensity measure types, different scientific applications. And we'll look to the OpenQuake Gsim library to see an example of this. So on the left is just the top part of the list for all the different GMPEs that are implemented in the OpenQuake engine. And highlighting Abrahamson 2014 from the former slide, the documentation here is indicating which intensity measure types this GMP can be used for, which tectonic region types, and the required distance measure parameter values and site parameters that are needed in order to use this GMPE. Okay, so this concludes the introduction to the ground motion characterization, and now we'll move on to the logic trees. So a logic tree is the construct used in PSHA that incorporates epistemic uncertainty. So start by understanding why uncertainty is important to consider in PSHA. And to do this, we'll reference a study from the 90s, which took a look at two different PSHA studies from reputable institutions that computed very different results for a critical site. And the main reason for this was because of subjective decisions that were made that impacted the outcome. And so in light of this, we can look at the two different types of uncertainty that have to be considered when these choices are being made. And the first is aleatory. And this is the type of uncertainty that's intrinsically related to the earthquake process. So that means that we actually expect this, we expect to see a range of outcomes for a certain source, for a certain ground motion. This is a type of uncertainty that cannot be reduced with more information. And usually this is incorporated inside of the hazard integral. So as an example, we're showing the hypocentral depth distribution for an example source in which there are 3 different depths that are expected to produce earthquakes for one given source. On the other hand, there is epistemic uncertainty. And in PSHA, this is handled using logic trees. So epistemic uncertainty is the result from our limited knowledge about a process, either due to limited understanding of the physics or mechanisms or due to insufficient data. And this is a type of uncertainty that is reducible as more information becomes available. So the logic tree is used to weight alternative hypotheses that cannot be excluded. So for example, entire seismic source models or individual source parameters, such as the maximum magnitude, the Gutenberg Richter values, or ground motion models. And the sum of the weights of each of these hypotheses is equal to 1. Each logic tree end branch is considered one realization of the hazard, and so it's a single evaluation of the hazard integral. An important aspect in developing logic trees is a sensitivity analysis that needs to be applied in order to avoid creating unreasonably large logic trees. And we'll cover this more in tomorrow's lecture on building a PSHA model. So a logic tree is hierarchical, and that means that it's a sequence of branching levels, and each one is representing a specific uncertainty. So in the plot here, we start with an initial model on the left. Consider a single faulting source, and to that source, we apply two different values of dip to the fault. So now we have, in the intermediate model marked in green, we have two branches. Then for each of those intermediate models, we apply two different seismogenic depths. And so by the end of these two branching levels, we now have 4 end branches, 4 realizations. So here's an example coming back to South Africa, for which each area source has its own logic tree applied. So the initial source, highlighted in blue, outlined in blue, is given 2 values of maximum magnitude and 3 values of A and B values. So in total, that reaches 6 values, 6 branches for that source. As you move from a nationwide analysis to a more specific, site-specific analysis, the source model logic tree could grow even larger. So this is an example for an analysis of one specific site that was of high priority, in which multiple different parameters within the MFD were considered, different styles of faulting, different dip directions, different dip angles, and the logic tree gets larger and larger. Moving to the ground motion side, this example shows the Gmpe logic tree for subduction interface sources in the Philippines. And in this case, there were 4 different GMPEs that were used to model the ground motions for interface earthquakes. And shown on the left here is comparative scaling of those 4 GMPEs for PGA for 1 magnitude 7.5. And as you can see, the GMPEs are they're attenuating at different rates, and they scale differently. And so these are important to consider in the case that different attenuation patterns or different magnitudes can't be ruled out. And again, we'll cover this more tomorrow in the building a PSHA model lecture. Okay, so this concludes the introduction to the components of a PSHA model. And so now we'll take a look at, once we put this model into a calculation engine, what are the primary types of results that are produced? So the 4 that we'll cover today are the hazard curves, so the native result of the hazard integral, hazard maps, the uniform hazard spectra, and a source model disaggregation. So the first result type here is the hazard curve, which is the primary result of the hazard calculation. And it's referring to a single site with a defined site condition and 1 ground motion parameter. So the plot is showing an example that highlights some of the concepts regarding hazard curves that are important to understanding the PSHA results. So just to orient with the plot, on the y-axis, we're showing the annual probability of exceedance, and on the x-axis showing the ground motion parameter level. And as the ground motion level is increasing, the probability of exceedance is decreasing. So in other words, more extreme ground motion levels are less likely to occur. The plot is showing 2 types of hazard curves. So there's the individual realization shown in gray, and the mean hazard curve, which is summing up all the weighted individual realizations to compute the mean hazard. We're also indicating some of the common probabilities of exceedance that are looked at for hazard curves. And again, showing that the more rare ground motions are larger. And just to keep reiterating the different expressions of PSHA, on the right here, we've shown how the probability relates to the frequency, and these different expressions are converted between themselves. So in some cases, you may be more interested in looking at the spatial distribution of ground motion parameter levels, but only for a uniform probability or rate of exceedance. So to do this, we use hazard maps. And the two figures here are showing example hazard maps for PGA with 10% and 2% probabilities of exceedance in 50 years. And these are derived by taking a single point on the hazard curve for each site and collecting all those points together until the map is completed. And what can be seen here is that as the probability of exceedance is decreasing, so we're looking at a more extreme or a less common representation of the hazard, certain structures that aren't as visible in the 10% and 50 years map are starting to pop out. The third type of hazard result is the uniform hazard spectrum. And this is used to show how the ground motion parameter levels change for different vibrational periods, again, for one site and for a uniform rate of exceedance. So in the example here, the values have been pulled from 3 different hazard curves, one showing PGA and then 2 different spectral periods. And these have been plotted together in order to form a uniform hazard spectra. These results are useful in cases when you're interested in the impact of the hazard on, for example, different building types with different natural vibrational periods. And the final type of result that we'll look at today is the hazard disaggregation. And these are useful to reveal which combinations of explanatory variables, so parameters used in the hazard input model, are contributing most to the ground motion parameter level at a site for a specific rate of exceedance. So looking again at that hazard curve and the single value for 10% and 50 years, we can see that there are different sources that have a larger impact on that computed value. And the 2 examples here are showing on the left the magnitudes and distances and how they're contributing. So taking the sources of each magnitude and each distance bin and summing up their impact on that computed value. And the second plot is showing which tectonic region type in terms of the latitude and longitude is contributing most. So in this case, the tectonic region type plotted in orange is having the largest contribution to the hazard at that site. So this reaches the end of the conceptual part of this presentation. So just to summarize, we've looked at the classical PSHA and how it evaluates the hazard integral. We've looked at the main components of the PSHA model and in the seismic source models, how they're used to represent all of the sources impacting a region, the attenuation relationships that take the ruptures and model the potential ground motion levels, and the logic trees that we use to account for the epistemic uncertainty. We've also looked at the outputs that are revealing the rates of shaking levels at each site and the spatial distribution and how this changes for a range of vibrational periods. So to finish up, I'll come back to the global seismic hazard mosaic and map. And I'd like to just give a brief overview of 2 models that we're in the process of updating now. And these are for the country of China and for the Dominican Republic. So starting with the Dominican Republic, This is a PSHA model that covers the island of Hispaniola, which sits close to the boundary between the Caribbean and North American plates. And this was developed as part of the TREC project that is currently ongoing within GEM. And this model gave us an opportunity to expand upon some of the standard methodologies that GEM is using to address some challenges within PSHA. So some notable aspects of this model are that the source model includes multiple different tectonic region types. So we have subduction interface and intraslab, as well as active shallow crustal sources. We were able to really hone in on the active shallow crustal sources using a database provided by our local collaborators of the faults, and also incorporating a methodology called sheriffs, which allows us to model the faults as a system as opposed to individual structures. So including multi-fault ruptures within the source model. And the active shallow crustal seismicity source characterization in this model includes 24 logic tree branches, and together the entire model includes 2,500. So to explain a little further what sheriffs is, I have a figure here on the bottom right that's laying out the source model, and I'll draw your attention to the red lines, which are representing the crustal faults. And in a standard methodology, each of these faults would be modeled as a single source, but in the real world, we've noticed that faults can link up together and rupture as multi-fault earthquake ruptures. And so zooming in on the inset in black here, we're showing how each of these individual ruptures has linked together not only one fault segment, the short segment that's centered in this box, but also some of the different faults to the east and west that are close in proximity to each other. Another place where this methodology, a similar methodology, has been used that you may be more familiar with is the Usurp model, which is a rupture forecast for California. Also to highlight the epistemic uncertainties that we've included here, we were able to include multiple hypotheses in the active shallow crustal component that helped us to observe a range of hazard results for the region of interest. And so on the left here, I'm showing how these epistemic uncertainties manifested into the magnitude frequency distributions for a single fault and its surrounding area that's close to the capital city of Santiago de los Caballeros. And to the right, we're showing the hazard curves that have resulted from this model, and they include the entire model, not only the models, or not only the sources that are representing this fault, but this is a means of depicting how using different magnitude frequency distributions can have an impact on the shape and the spread of the individual hazard realizations. The second example is the PSHA for China. And this is, again, an opportunity to advance some of the methodologies that we've been developing at GEM or exploring. And in addition to using sheriffs to produce multi-fault ruptures, complex ruptures, China is an area where there are many known faults, but not as many known slip rates. And so this was an opportunity to use a tool being developed called Euler, which is using GPS deformations in order to model the slip rates on the faults and use this as an input to sheriffs. And in addition to using these modeling outputs, the earthquake rates are constrained also by the earthquake catalog by using them to compute local MFDs surrounding the faults as well as the B value, so that rate of high to low earthquakes. While the results of the fault and rupture modeling are important, the background seismicity, the distributed seismicity in China, is also quite important to the hazard. And so the two source types have been balanced together to produce a model. So on the right here, the bottom plot is showing the rates of the distributed seismicity sources. And to the top, in the top plot, this is the hazard output, the peak ground acceleration that has come out, the preliminary results for this. So the last two models that I introduced are a bit more of advanced models, but they give you a little bit of information for what to think about while we go through the content tomorrow in the building a PSHA input model. So just one more preface to that lecture for tomorrow. So I'll close by providing some additional references for introductory information for PSHA, as well as some of the underlying concepts that are available. And in particular, I'll point to the Trek PSHA training manual that was recently developed and is complemented with some interactive examples. This is also part of the project, the Trek project within which the Dominican Republic was developed. And with that, I'll take your questions.
Thank you, Kendra, for your insightful talk on probabilistic seismic hazard analysis, starting from basics of seismic hazard to different output of hazard analysis and hazard calculation for different parts of the world. A huge thanks to you, Dr. Kendra. Now, may I request our session chairman, Professor J.R. Kyle, for his comments. Over to Professor J.R. Kyle.
Okay. It was such a elaborative and such a detailed information and so much educative, Dr. Kendra. Really, thank you so much. I think all participants are much benefited with your detailed explanation. I have a layman's query.
Okay.
Yes. How the PSHA, means probabilistic hazard analysis, and deterministic hazard analysis are compatible?
Yes,
in terms of global scale and local scale. What is your comment on that?
Sure, that's an important question because there is ongoing debate that may never be settled on which is more appropriate to use. Deterministic hazard analysis often is considering specific scenarios. For example, the worst possible scenario of an earthquake that could occur. And so these are considering specific earthquake ruptures as opposed to all of the possible earthquakes that could occur. And so depending on the application, there may be some variability, but the probabilistic method is more useful in instances where there are many applications, for example, different types of buildings being looked at, where the recurrence at multiple different investigation times is of interest, as opposed to, for example, a critical analysis. Additionally, there are instances in which the probabilistic method is more useful for example, risk calculations pertinent to insurance, so monetary aspects like that, in order to prepare for things of this nature.
Oh, thank you so much. Thank you so much for so nice answer. Thank you. Over to Santanu now. If there is some questions, please go ahead with the questions.
Sure, sir. Should I go read out the questionnaire?
Sure.
Okay, ma'am. Thank you so much for such an giving us deep insight about the probabilistic seismic hazard analysis. So I am going to read out the questions from the participants across the globe. The first question will be, can recurrence period of earthquake be vital criteria for forecasting and seismic hazard assessment?
I'm sorry, can you read that one more time? There's a little background noise.
Sure, ma'am. Can recurrence period of an earthquake be a vital criteria for forecasting and seismic hazard assessment?
Sure. So, for example, the characteristic magnitude frequency distribution typology is often based directly on that expected recurrence, whether that is coming directly from the recurrence value or coming from a slip rate that's used to resolve the recurrence value. So for sources that are thought to behave in recurrent ways like this, that would be the way that they're incorporated into a hazard model. Does that answer your question?
Surely, ma'am. The next question will be, in the real world setting, can we consider earthquake to be random phenomena, or does it satisfy stationary condition? As stationarity plays a prominent hypothetical standard for probabilistic analysis of seismic data.
Yeah, this is another one of the large challenges in PSHA, is that we tend to assume stationarity, and this is the easiest way to model the sources, but we do acknowledge the contrast between what is sometimes seen in nature and the principles that we use to model. There are some more advanced modeling approaches that consider time dependence, or that also consider clustering. And so these address some of those shortcomings.
Thank you, ma'am. The next question will be, can OpenQuake engine format be used for classifying subduction zone seismicity?
Yes. So within the global hazard mosaic, since we're covering the full globe with those models, a large number of them are including subduction sources. And in terms of actually characterizing the sources, the toolkits that we develop and maintain are more useful for actually constructing the sources, but ultimately they will be represented in the OpenQuake engine format so that they can be part of that input model. And I think that following tomorrow's lecture, and especially following the lecture on Tuesday on the OpenQuake engine, that the mechanism for that will be more clear.
Thank you, ma'am. There are a lot of questions. The remaining questions we are going to email you. If you don't mind, you can answer them by email.
Okay.
Thank you.
Okay. Thank you. Yeah.
Thank you, Prasija, and thank you, Kendra. Now over to Mr. Novosity Modia for vote of thanks.
Thank you, sir. A wonderful evening to all from colorful India. With the end of today's session, it is my utmost pleasure to heartily thank whole IBWGST 2021 family. I would like to grab this opportunity on behalf of entire CSR NIST family to thank Dr. Kendra Johnson of Global Earthquake Model Foundation, Italy, for her generous acceptance of our enticement to address on Introduction to Probabilistic Seismic Hazard Analysis. Once again, very heartfelt appreciation to Dr. Johnson for the vital information you have shared with us. Furthermore, I convey my sincere regards to Director Dr. G. Narahari Sastry of CSI NIST Johat for his stupendous commitment and implication to successfully organize the live session meets. Thank you once again, sir. I am also privileged to heartily admire international advisor of this workshop, Dr. Andrew J. Michael from USGS USA, and session advisor Professor Dapeng Zhao from Tohoku University for their rigorous support towards the event from its start for a great success. I would also like to applause from zenith of my heart to Professor J.R. Kyle, sir, session chairperson, and co-chairperson Dr. Saurabh Barua, chief scientist CSIR NIST, for their thorough obligation towards the event to be successful. We are also fortunate to thank our special guest, Dr. Shreyasi Chandrasekhar of GEM Foundation for their gracious presence. It's my privilege to thank Dr. Santanu Barua, convener IBWGST 2021, for his lively cordial fidelity towards the program. We once again, from the bottom of our heart, thank him a lot for introducing this medium to get together with laudable personalities from different countries. On this occasion, I express my sincere thanks to all the attendees for their dynamic involvement throughout the sessions. We, with huge expectations, are also looking forward for tomorrow's session sharply at 10 a.m. Indian Standard Time. The speaker for tomorrow's session is Dr. O.P. Mishra, Director, National Center for Seismology, MOS, Ministry of Art and Science, India, with his lecture on seismic micronization, an efficient tool for earthquake risk resilient structures. As a concluding remark, Namaskar aru dhanyabad, with best wishes and love from Assam. Thank you. Thank you, ma'am.
Thank you.
Dr. Kendall, thank you so much for having with us.